Hi everyone. So here we are again, and we're still traveling along on our redox journey. So far, we have practiced determining oxidation numbers and writing half equations and balancing those in terms of paying attention to what's going on with our electrons. And that's great. Hopefully, we're feeling more comfortable with that. But we do need to figure out how we're going to use these. Why are we so interested in actually using these half equations and figuring out what's going on? So today's video, we're going to take a quick look at redox titrations, some of the applications that we have for it, and there'll be a second video coming up on the Winkler method, which is a particular reaction we need to know a lot about for our prescribed practicals. So basics of the theory today, and we will review volumetric techniques when we're in class, but let's get started. So the learning objectives for this video are being able to explain why most redox titrations don't require indicators, being able to use half equation balancing method to balance a redox equation and then apply this to volumetric analysis to figure out the concentration of an unknown, so basically titration questions, and then be able to list some of the common oxidizing agents that we use in redox titrations and know their color changes, so that when a reaction is described to you in a question, you pretty much can figure out what's going on straight away. So let's get started. Essentially, redox titrations follow exactly the same process as an acid-base titration. So we're going to have a conical flask at some point, and inside that conical flask, we will have an aliquot, and then we will also have a burette filled with another solution. So these follow the same process as an acid and base, but this time we've got a redox reaction happening in our flask rather than an acid-base neutralization reaction. So we still have pipette, burette, volumetric flask, all our standard titration glassware, but we are looking at some different processes. We don't always need an indicator because these solutions, such as MnO4 minus, change their color on their own when we reach the equivalence point. So remember, with acid and bases, we titrated to an equivalence point where the indicator changed color. With redox reactions, a lot of the time the oxidizing reagent, when it's reduced, will have a different color form, so we can see the end point without having to use an indicator. These titrations are used for a number of things, quite often a lot in food chemistry. So in determining the amount of sulfur dioxide or even the amount of ethanol in wine, looking at vitamin C content in fruit juices or in vegetables. Some of you may look at using a vitamin C titration for your IA, for your investigations. We can use them for determining the concentration of bleach, or hydrogen peroxide, even figuring out how much chlorine is in pool water. We can use them for these kinds of things. We follow exactly the same concentration calculation processes. So we will be looking at things along the lines of being able to use our concentration being equal to number of mole divided by volume, but we will have a look at that. So these are some of the common oxidizing reagents. By no means are they an exhaustive list. So there are other ones other than these. These are some of the most common ones that we will see in the lab. Okay, so acidified permanganate ions, so manganate 7 ions, telling us that the manganese is in an oxidation state of +7. Okay, and we should be pretty familiar with this reaction already because this is a half equation that we've practiced a lot in the last few days. Okay, so we're looking at this MnO4 minus aqueous, and then the 8H plus with the 5 electrons, Mn2 plus and 4H2O. Hopefully you're pretty confident with balancing this one. Remember, we would usually start off with the permanganate ion going to the Mn2 plus, which is its reduced form, and then we balance by adding H2O, H plus, and then balancing charge. With the permanganate ion going to Mn2 plus, you should always end up with 5 electrons on the left-hand side because it's being reduced, and that's a quick way to check. So the other one that we've seen a bit over the last few days is this acidified dichromate 6. okay, which gives us the 6 electrons on the left-hand side going to the 2 chromate ions. Now, permanganate is this dark purple color that we see over here on the right normally. Okay, so it's a very, very dark purple color. As we decrease the concentration, it will go through to a light pink. When it's fully reduced, so the manganate 7 ions are dark purple, the manganese 2 plus are actually colorless. So we can tell we've reached the end point when the pink persists. Okay, so if you think about it, we're dropping the purple solution in, it's disappearing as it reacts, turning clear, turning clear. When we reach the end point, that one drop of pink will no longer react. So it will stay a very faint pink color, telling us that we've reached the end of the titration. So the end point will be indicated by a pink color, even though the reduced form of the manganese is colorless, okay? Because it means that there's just that little bit of manganese left over, which can no longer be reduced, so we know that whatever we were titrating against has all been used up. Okay, so in the case of the acidified dichromate, we've seen this when we talked about the oxidation of alcohols. We could tell if we had a primary or a secondary alcohol by adding acidified dichromate, and we said that if we had a primary or secondary, we would see the reaction go from orange to dark green. So that is this reaction here occurring. Okay, so what we're actually looking at is the dichromate, so the dichromate 6 ions turning into the Cr3 plus ions. Okay, so what that does is go from orange to green. So this Cr3 plus is going to actually be a green color, and the dichromate is orange. Okay, my computer seems to be still flaking out a little bit, so it's not allowing me to write. So hopefully we'll be able to go through the example, but we'll see how it goes. The other one that we look at is iodine. And if you do biology, you may have seen this one already. We use iodine in combination with a starch indicator because iodine, I2, will be this brown color, and then the I minus, sorry, this is going a bit crazy when it's writing all over the screen. The I minus is this yellowy golden color. So this can be a little bit hard to tell the difference between, particularly at low concentrations. But when we add starch, that starch reacts with free iodide or free iodide ions, and we get a deep indigo blue color. When all the starch complex is broken down, it goes clear. So we tend to look at this dark blue versus clear reaction that you see, and this is when we have the addition of starch in it as well as the iodine. So while the iodine is coloured, we get a better reaction when we have iodine and starch solution. Okay, let's see if we can get this to work. So this is our example question. We have a 10 centimetre cube sample of white wine and it's being placed into a volumetric flask. From that, we're adding water to make it up to 100 ml solution. Okay, so we're taking an aliquot of our wine. If this is going to let me annotate, we're taking an aliquot of our wine, and then we're going to dissolve that up into a volumetric flask. Let's see if I can actually do this in a way that we can see. So we're going to have a 100 ml flask here. Okay, and we've taken 10 mils of our wine and placed it into the 100 ml. So we've got a 1 in 10 dilution here. Okay, then 20 ml aliquots of this are transferred, and we're going to titrate these against 0.1 molar acidified potassium dichromate. So this is going into our burette, okay, and we're taking 20 mils of these solutions into our conical flask. The mean titer, so the average volume that we got from our burette, is 24.61, and we're asked to calculate the concentration of ethanol in the sample of white wine. This is the very prep that we will be doing in our double, except that we'll be titrating to find the amount of sulfites, not the amount of ethanol. Okay, so in order to do this, we need to have an equation. Hopefully, you can have a go at writing what the two things are. We've got acidified potassium dichromate and we're looking for ethanol. So we've got ethanol reacting with acidified potassium dichromate. So you will notice that we will have this, and this will be one half equation, and then this and this will be the other half equation. What I want you to try and do is have a go at balancing this according to the half equation method and see if you come up with the overall equation. In this case, the overall equation has already been done for us. Okay, so I'm going to pause this, get myself set up, and then go through the solution for you. If you think you can figure out how to do this, have a go, and then just come back and check if you've got the answer right yourself. Well, hopefully you had a go, and if we scroll all the way down to the end here and you worked out that the concentration of the alcohol was 1.85 moles per decimeter cube, congratulations, you probably have a handle on this. I'll upload some more questions for you to have a go at, but great work. If not, stick with me. I'll talk you through this example. Unfortunately, the annotation pen isn't working, so I've typed it up and we will go through it bit by bit. So first of all, we're going to gather together the information that we know. So the question has told us that the concentration of the CR2O7 2- solution was 0.1 moles per decimeter cubed for us. Okay, so we've pulled that information together. We've also been told that the volume of the dichromate solution was 24.61. So these two things here are actually from, if we look at it, we're getting these two values from this solution here, the dichromate solution, and the mean titer that we have here. Okay, so that's where these two volumes, these two pieces of information come from, and there's our concentration there. So they all come from that bit there. So that's our volume and our concentration, which means that we can work out the number of mole of dichromate that was delivered from our burette. So we remember that we know that N is equal to C times V. So we're taking our number of mole is going to be equal to our concentration of dichromate, the 0.1, multiplied by our volume of dichromate, remembering that this is in, for us, this is centimeters cubed, and we want to convert this into decimeters cubed. Okay, so we have 0.1 times 0.02461, which gives us 0.004261 mole of dichromate. Okay, so that was what was delivered from the burette. Then if we look at our equation, we can see here that we have dichromate is what we found, okay, and we want to relate that to the amount of ethanol. Okay, so if we look at here, the ratio of ethanol to dichromate, so this is what I want. So remember, a ratio of what I want over what I've got. So it would be 3:2. So if we multiply our amount of dichromate by a ratio of 3/2, that will give me the number of mole of ethanol. Remembering we take the number of mole of what we know and multiply by what we want over what we've got. So we will multiply by 3/2, and that will give us 0.003692 mole of ethanol. So for that amount of dichromate, that is the amount of ethanol that must have reacted. Okay, so that's how much was actually in the conical flask. Okay, so if you remember from our question up here, so this is 20 ml aliquots of the diluted wine. Okay, so if we take this, let's see if we can highlight it in a different color. It's not going to change for me. So that's 20 ml aliquots of the diluted wine. So this is the wine where we took that 10 ml solution. We took the wine and we've taken 10 mils of wine and then diluted into a volumetric flask. Okay, so this is the diluted wine. So this is the number of mole that is in our diluted wine. So it was taken from a solution of 100 ml. So remembering that 20 ml goes into 100 ml 5 times. So the total number of mole in that flask would have been 5 times what we get in the 20 ml. So the number of mole in the volumetric flask will be 5 times our number of mole in just 20 ml. Okay, so because we've diluted, the number of moles that we had in the flask is going to be equal to the number of mole that was in our wine. Okay, so the amount in the original 10 ml sample is going to be this number of mole because that's the number of mole that we diluted up. Okay, so now we can work out the concentration of ethanol in the original wine because we had this number of mole in the original 10 centimeter cube sample. So we get our concentration is equal to N on V, and we get 1.846 moles per decimeter cubed. Okay, which is the same as 1.85 molar. Hopefully you can follow that. If not, ask me the next time I see you, which will be tomorrow morning when we go through volumetric analysis, and we'll go through this again. Remembering that in order to do this one, we had to first balance our redox equation, which means that in this kind of question, you would have to start with the first half equation. Other than that, it's a straight volumetric analysis. So good luck, and we will definitely be practicing some more of